Hey there, welcome back to the AtroKraft Satisfactory Megabase project. Last time we finished the Parthenon structure, every column, floor, and light is finally in place. The stage is set for it to become the heart of production. Now it's time to bring the machinery in. In this episode, we start putting the building to use, moving from structure to function. Aluminum refinery takes the spotlight first, linking together the systems we've been preparing for since the early game. From alumina to scrap to ingots, each step builds towards full-scale output and unlocks the tools we need for the next tier. Once the aluminum is flowing, we'll pivot for a moment to shift to copper ingots and figure out the factory logistics, before finally coming back to aluminum and finishing our first complete production chain. By the end of this episode, the factory won't just look impressive, it'll be alive with motion and purpose. So let's get to it. We started with the sloppy alumina recipe, an alternate that skips the silica byproduct entirely and gives a tighter yield from our bauxite. From there, the alumina solution is combined with petroleum coke using the electrode aluminum scrap recipe, which pushes the efficiency even further while keeping the system clean and predictable. Of course, that combination brings one big problem: excess water, and more than the system can handle on its own. At first I planned to sink all of it into wet concrete production, but that would have required a mountain of limestone. So the next attempt was to reuse the water by routing it back into the alumina refineries. But that quickly led to pressure buildups and slowdowns that choked off scrap production. So, the secret sauce wound up being a hybrid system that blends both ideas. I put in a diverted overflow line that lifts a section of each line up to the level of the 10-meter head lift the refineries provide. Then I routed that line into a single wet concrete plant. This setup means that under normal operation, the reclaimed water flows level back into the alumina refineries for reuse. Only when the line fills to capacity does the overflow kick in, diverting the excess through the lifted section of pipe towards the wet concrete producers. That elevation change, the 10-meter head lift, acts as a natural regulator, preventing the kind of pressure saturation that would otherwise stall the aluminum scrap production. Downstream, the main loop continues to supply the alumina refineries. Flow valves fine-tune the balance between fresh intake and reclaimed water, keeping the ratios precise. In theory, if the refineries ran continuously, that wet concrete backup wouldn't be necessary and every drop would be reused. But production isn't always perfectly steady, and when the machines stall, that reclaimed water needs somewhere to go. The overflow line provides exactly that, a relief path that keeps the pressure from building up and the system from choking itself. So, once the scrap is flowing, it's smelted into ingots using a simple high-throughput array of smelters. Nothing complicated here, just clean, consistent conversion that turns the upstream chemistry into usable metal. With that final link in place, the aluminum chain from bauxite all the way into ingots runs smoothly and continuously. Once tested, that small bit of engineering finesse concerning the water excess made all the difference. No backups or stalls, and for the first time, a completely stable aluminum loop running at full capacity. With aluminum now running smoothly, we set up a small temporary outclad aluminum sheet line. Just one machine quietly chugging away, feeding its output into dimensional storage. It's not built for volume, just convenience. Enough to stockpile materials for logistics upgrades before we moved on. From there, we pivot momentarily to focus on copper, easily the single largest resource demand in the entire Parthenon plan. The numbers are not small either. Over 4,000 ingots per minute, all produced using the pure copper ingot recipe, which calls for refineries and not smelters. The plan calls for 107 machines, but to make the math clean, we built for 120 total. This will keep our belt values consistent, and also some over-engineering at this stage is not undesired. So, each block of 20 refineries feeds into a shared belt running 720 ingots per minute. Altogether, that gives us 6 belts with a little over 4,300 per minute total, fully saturating the copper flow for all downstream usage. The challenge, though, is space. The subfloor beneath the Parthenon isn't flat. The dunes rise and fall, forcing creative placement to make the layout work. So by staggering machines and threading pipes through whatever gaps we can find, we managed to fit the full complement of 120 refineries into the available footprint. It pushed the limits of the space, but it worked. And with that, the Parthenon's copper backbone is finally online. Now, to route all that new copper and aluminum into the Parthenon's production floors, the next step is logistics. We began by running each of the main output belts up vertically through the train floor, just inside the train loop. From there, every line passes directly into the interior of the columns, which act as vertical transport shafts for the entire factory. This system works beautifully thanks to one simple trick. If two conveyor floor holes are aligned vertically, a belt lift can connect them over any distance, no matter how tall the structure. That meant that we could drop from the very top of the Parthenon down to the lowest subfloor in a single continuous lift without intermediate junctions. With that in place, we finally had the layout we had envisioned early on. Resources entering from the ground, flowing upward through the columns, and then descending through each production floor step by step. It's a clean one-directional flow from top to bottom and sets the foundation for the fully modular production chains that will fill the Parthenon in the episodes ahead. With the resource lines now routed into the Parthenon, the next step was putting that flow to use. We're going to be starting on the second floor, where most of the high-end electronics and composite materials are going to live. The first of these was alclad aluminum sheet production. Our plan calls for 34 assemblers, so we created a modular design, one skid with 16 assemblers, stacked twice for 32 total, and then overclocked one machine on each skid to 200% to bring the total output to spec. Each row of 8 assemblers was placed as tightly as possible, enclosed in a full steel framework, forming a complete self-contained assembly. These skids are not just aesthetic, they're functional. In industrial design, these compact frames act as black boxes, modular process units where the inner workings don't need to be micromanaged. What matters is that the system's inputs and outputs match their target performance numbers. The same philosophy applies here. If the per minute input and output numbers on the signs match spec, the skid is working as intended. If the numbers are off, it's a sign of a local issue, not something buried 5 systems deep. To verify the skid before integration, we connected the outputs to sinks and ran it under full load. Bringing one block online at a time keeps troubleshooting focused and prevents cascading errors later. I can't stress enough the importance of testing at this stage. It's not about efficiency, it's about certainty. By treating every production block as its own black box and confirming that each one performs to spec before moving on, we guarantee that when the Parthenon finally runs as a whole, every part of it will already be proven stable and reliable. Down on the first floor, we built what will become the hall of storage, the central collection and upload point for each resource produced within the Parthenon. The layout is simple, a long illuminated hallway lined with industrial containers, but the atmosphere feels fitting for the scale of this project. Each container is labeled clearly with both the item icon and its fill rate per minute, making it easy to monitor production flow at a glance. And above every container sits a dimensional uploader, linking the Parthenon's output to global storage so we can access materials anywhere in the world. We don't yet have enough Mercer spheres to fully populate every uploader, so some resource slots will have to be rotated as production expands. Still though, seeing the hall come together is deeply satisfying, for this is the point where everything built above it finally has a visible destination. And concerning aesthetics, the Parthenon really needs a proper centerpiece. Realistically, I'd love to place a statue of Zeus here, towering over the hall like the original temple, but that's probably something only a mod could make possible. For now, it'll most likely be the alien power augmenter, standing in as our symbolic heart of industry. And with that, I think we're going to call it for today. This episode brought the Parthenon to life in a real functional way. Aluminum production is stable, copper is running at full capacity, and we started defining how materials move through the factory from top to bottom. On top of that, the first production skids are built, labeled, and tested, and routed down into our hall of storage, which is also finally taking shape. Next time we'll be expanding fast, filling the rest of the floors with production for electronics, advanced materials, and high-end parts. We will be focusing on one production chain at a time, installing skids, feeding them, testing, and finally routing them through to the main storage hall. Item by item, the Parthenon will be coming alive. As always, thanks for watching episode 6 of the AtroKraft Satisfactory Megabase project. Don't forget to like, subscribe, and check out the Twitch streams where all of this is built live. We'll see you in the next one.